Hope you all had a good evening yesterday. I see, I see a little bit of the Connect effect already happening. So welcome to the second day of Connect. Check the schedule for any late changes. I'm not aware of any, but it doesn't mean to say that there aren't happening. So today I'm going to introduce our speakers, but first of all, a quick notice. So at 11:10 today, we do have a session called Ask Arm Anything. Cancel it. Just, I'd like to say that session is open to Linaro members, so company members of Linaro, and companies that have an NDA enforced with ARM. And we will be checking badges on the door. Our firm but fair Linaro security team will be there. So please be patient as we check your credentials. So without further ado, I'd like to introduce our first speaker, who is Sergi Mansilla, VP of Engineering at Edge Impulse. Sergi.
Thank you. Thanks a lot. My first time at Linaro Connect won't be the last. So I'm here, let me introduce myself first. I'm amazed how well it works. Kudos to the production team. I'm the VP of Engineering at Edge Impulse. I don't know if many of you know Edge Impulse. We're an Edge AI platform. I've been around for a while, 20 years of experience, or, I'm old, basically. I always been involved in one way or another in building developer tooling. I was involved in IDEs before. Now with Edge Impulse, we're doing another kind of developer tooling. I've been involved in several open source projects on Firefox OS, distributed systems. I've been a little bit around everywhere. I also wrote a couple of books. I don't recommend it. Now, enough about me. So 2 things about this talk. We're going to talk about Edge AI and what it means to be a platform in Edge AI. So let's first of all define both concepts. Edge AI, it's actually very well defined. In fact, there's an acronym called BLURB, which involves the first letter of some of those words. But let's go through each one of the 6 items. Edge AI happens if you have any of those needs, you're into Edge AI. Bandwidth and latency. If you don't have either much bandwidth or latency, you probably need to compute or to run AI on device, because sending it away or waiting for responses from the cloud or from any other connection might be very hard, very slow, or plain impossible if you have devices out there in the field. Privacy, that's a big one, not only for users. Privacy many times gets talked in the context of individuals, but companies also. We're at a moment, as you know, with ChatGPT and other AIs, everything we ask the AI goes to some cloud servers and gets back to us, but we don't know what happened to that data. Is it used to train? Is it used to sell as ads, etc.? So in the industrial setting, companies are even more concerned about that. Are you sending your IP out there to be processed by what? So privacy, power, devices that are out in the field are very power constrained, usually on batteries of some sort. If you start sending data back and forth, you're going to run out of power very quickly. Economics, saving storage and compute costs. You don't have to send the raw data, store it, verify it. Reliability, be operational. Always you're independent. Your device is self-maintained. You don't require any third party, any third server. And then innovation. By reducing your device, you can do more things with it, like the Aura rings and stuff like this. By putting all the smarts inside a single ring, they're not constrained by anything else. So you can be more creative where you take your data and where you use it. Let's define a little bit also edge AI. What did we do before? Like IoT existed many years before the current wave of AI. But I'm sure that you also have that feeling. IoT had this boom, but then nobody knew what to do with it. So it exploded. It became big, Arduino and all this. So it is there, but when it came out, it was supposed to be like the future, and it kind of struggled a little bit. The reason was that when the main basic cases were covered, there was not that much usefulness because of the constraints, right? Not much connectivity, not much battery, and so on. So you're very constrained. That was because we were programming in a traditional way, set of rules and data, and then learn from what you observe, adapt the rules, and by adapting the rules means like creating the heuristics yourself as a developer, as an engineer. So it's very time consuming and very involved, and of course you miss a lot of the anomalies. With artificial intelligence, you don't focus on rules, you focus on outcomes. You don't say like if this then that. You say like I want that outcome. I want let's say. Tell me when something is wrong. Tell me when, just before I was looking at a project that somebody sent me that's done with an NVIDIA Jetson Nano, I think. And it's basically a device that just by filming or by videoing a surgery room, it can tell whether any surgical instrument has been left in the patient's body, which is actually kind of a more than it's not that crazy to happen, which is it's concerning. But if you were to encode that into rules, so you have a camera and you know, with computer vision, with whatever, but you have to program, okay, make sure that that no surgical instruments are left in the body of the patient. That's a nightmare. How would you cover it? Even if you manage to have some success, there's too many edge cases, there's too many things. AI can deal with that. So AI plus IoT kind of creates this edge AI revolution. And then you can get into any industry. It's like a worldwide phenomenon. Our customers involve like from health appliances, from health devices to industrial devices, asset tracking, predictive maintenance, which is the biggest one, in industrial, in home appliances, etc. Obviously, I work for a company that does edge AI, but it's not me saying it. There's a definite trend of edge AI becoming big, because why wouldn't it? Right, once you manage to make these devices efficient and being able to do AI compute, you have a lot of possibilities. And in fact, so much so that at the moment it seems like cloud AI, what we see on the news, what we see all the ChatGPT revolution or rivals and so on, are going to be the norm, and edge AI is that niche. But my bet is that in 5 years, in 10 years, edge AI will be the norm, and cloud AI will be the exception for massive stuff and data sets. And the reason, and it's already starting. These are three news articles about Apple that are coming, that came like recently. Basically, all the companies are starting to put smarts on the phones. Apple, just to put an example, there's others, but Apple is very visible, obviously. They're ramping up their chip production, their NPUs, their GPUs in the on-device. They're gonna have AI on the phone, and that is edge AI, basically. So edge AI will become the norm in the future. The traditional approaches up until now, they haven't worked, because the real world is very fuzzy. Heuristics are labor intensive, and insights are being left on the table. And this one I want to focus on. The picture you see is of an anomaly in a cinder block, and these insights cannot be programmed with traditional heuristics easily. And right now, we're leaving them on the table by discarding this data or by not knowing that this data is there. And I'll get back to this in a second. What are the current challenges? So up until now, even if devices manage to do AI or to have some connection to some AI compute, what we observe and what other companies observe is that 99% of all the sensor data that happens or that a sensor can gather that a device has is discarded, because you cannot be sending it back and forth. You cannot operate on it. You cannot compute on device. You haven't been able to up until now. So all this super valuable data from not one sensor but multi-sensor, sensor fusion devices and so on is discarded just to get, you know, a small sample in the window of sensor data that you operate with. What we want to do is use all the sensor data, and the way we do that is the device processes it on its own, doesn't miss anything, and you get much more granular insights. The tooling, current ML tools are not designed for edge AI. Current ML tools are designed for big AI. They're designed by Google, by other companies that are not interested or have not been interested in edge device yet. And that makes it very, very hard, because the constraints and the needs for edge AI are radically different than for LLMs or for large models. And the infrastructure complexity that it requires. So this is one of the things. Edge AI and devices and processing is one thing, but the elephant in the room, or the important part, really is the data. AI, whether it's large AI, edge AI, data is the important part. Handling that data, storing that data, versioning that data, verifying it, cleaning it, it's massively complex, and it doesn't have to do much with AI itself. But maintaining large data sets and ensuring that they are relevant, it's very hard, especially for companies who are not specialists in that. Now let's go for a platform. We define a little bit what we're talking about when we talk about edge AI. A platform is extensible. A platform is a tool for people to get from point A to point B, but it has to be extensible. It has to allow users to create stuff inside the platform that was not there to begin with. It has to provide a suite of different services for the same domain. It has to be multi-user, so people can collaborate, can send stuff, can talk, and can modify other projects. Interoperable. You cannot create your own bubble. You cannot be like, hey, I created this, has nothing to do with anything else, come use it. It has to meet the users where they are. It has to integrate with existing tools, etc. It has to be scalable. Obviously, if you have especially if you have big data for AI. And most importantly, it has to promote an ecosystem. It has to engage developers. It has to make people use it. Otherwise, it's dead in the water. Create community. I will add a couple. A platform meets the users where they are. What we found at Edge Impulse is that there's no single kind of user that is involved with Edge AI. Everybody has different needs, maybe they have a model. They're very good at making models, but they're not good at maintaining it, at deploying at devices. Maybe you're an embedded engineer with years of expertise, but ML is kind of still a strange beast to you. Or the other way around, you're a data scientist, know everything about ML, but doesn't understand how constraints work in the embedded world. A platform creates a mental model. You don't only provide a set of tools and like, here you go. Through metaphors, through decisions in API making and others, you create a mental model so the users understand or have a flow in their working. Similar to, if you think about GitHub, The tool is Git, we all know it, but GitHub on top of it built a flow that we're all, or GitHub or GitLab, whatever you guys use. It created a flow that is inside your head is a mental model. Like you submit code, there's a PR, there's a review, I could run it through GitHub Actions or whatever, and now it gets deployed. It feels natural and it feels normal because it works and we're used to it now. A platform abstracts complexity. So a platform basically, if it's worth anything, is taking many tools, making them work together, and by definition, abstracting the complexity from that tool, from those tools. In AI and Edge AI, the complexity is insane because you don't only have all the vendors, all the different languages, the different infrastructure connections between where the data is, where you deploy, device orchestration, and all this. You don't want the user to have to deal too much with this. You want to abstract that. And a platform can be opinionated, sorry. A platform, by being an expert in the field, can be opinionated about entire areas of the domain. An example on Edge Impulse is like, we don't provide example data sets, for example. What we do is make it extremely easy for users to provide their own data set in real time. Like if you go to Edge Impulse now, you can, from your computer, create voice detection program in a second by using your computer's mic or anything. The reason for that is we don't want people to bring a random data set they know nothing about, they haven't created, try the tool, kind of get insights that they're not relevant to their interests, and they don't know what to do with. It has to be your own stuff. It has to be something that you're involved with in some way to understand how it works. This is a quick screenshot of our platform of Edge Impulse. This is all we do. So I think that we can call ourselves a platform. We take you from point A to point B. We offer all the tools necessary. We currently have around 120,000 developers and 300,000 projects. We collaborate with a lot of brands in the sector. We have a lot of silicon partners. I see my time is running out, so I'm going to accelerate a little bit here. This is Edge Impulse, basically. What we have several phases: data collection through edge device, data upload from your cloud. We acquire valuable data securely, enrich data, validate, and deploy. What do we deploy to? Devices, C++ libraries, embedded Linux, mobile and web through WebAssembly, etc. Any sensor, we go from ultra low power to crazy GPU, Jetson Nanos style devices, and we try to make everything work as much as we can as in low power devices. Comprehensive hardware support, and I don't want to get too much into this, but yeah, I mean we benefit from all from the silicon ecosystem. We have a Neon compiler that I'll talk about in a minute. You get access to all the source code and so on. And now let me go through the talking points because I want to get to the good stuff. What we've discovered along the path of creating a massive platform that is successful. The first one is, you don't. Oh no, I didn't get that. You don't know what you're building at first. That's what it should say then. Silicon vendors, when we deal with silicon vendors, it's amazing to see because you would think that they have their processes very, very streamlined and very understood. But very often what we get is not a completely finished product that we have to finish ourselves. You go to a silicon vendor, gives you some hardware, and it tells you like, oh yeah, this runs AI, has a neural accelerators, runs all the models. The truth is, they tested a model once, it's an old model, and they call it good. We need to make it work for all models in all devices. So we have to do a lot of work on our libraries to get there. Or another real case, like when we get to test the audio processing on the finalized piece of hardware, there's no microphone, and we go back to them, and they didn't know. So their test processes are not amazing, and we have to adapt to all this and make it work inside our platform. The second thing we found out, or that we learned, is that you start from the basics to make it work. In our case, that was optimize C++. We write C++ to convert Python models from TensorFlow, TensorFlow Lite, TensorFlow for microcontrollers, translate them into C++. This runs everywhere, in every device, every MCU, every MPU, everywhere. And then we take it from there and we upgrade it when a device requires it. We have an MPU, good, we'll use it. We'll have a GPU, we'll use it. But our baseline SDK works everywhere. And that simplifies things a lot. That's the way, that's how we manage to be compatible with a lot of devices. At the very least, you have the C++ baseline. Then afterwards, we build it from there for each device. We generate optimized C++ libraries. A C++ library, the same one, exact standard C++, can run on an MCU, can run on a Mac, can run on embedded Linux, anything. We also have, we created the Eon compiler, which reduces further basically what it does is the process of taking a TensorFlow, a Keras model into a pure C++, optimize it for RAM, which is what customers need the most. The feeling is to optimize for CPU always, performance, but actually CPU is cheaper than memory in our field. So we created a compiler that does that. And now I wanted to get into a bit of a story, into a concrete example. So there's two big parts in in creating edge AI inference or models on these libraries that we spoke about. There's the DSP part, the signal processing part. We have a team for that, and there's the ML part. Usually, the easy part is to use ML to do everything. It's very, very powerful and easy. But it turns out, for example, with FFT, fast Fourier transforms, which are very used on DSP, are much, much, much more efficient to do by hand, to do with known algorithms, than to let a neural network figure it out, which is what is pretty much done everywhere. So we use DSP to do that pre-processing and then send it to the neural network. We save a couple of layers and makes it very fast. The naive ML approach works, but it won't work in many devices. It just works as in you want to test it, fine. That has become very important in our time series analysis. So for example, just to put an example, if you replicate FFTs in pure ML, you might require n to the square weights for training. So for a 256-point FFT, which is something average, FFT, you don't need additional training weights later on in the neural network. With pure ML, you would need 65,000 weights that the neural network has to go through, spend more memory, do more processing, etc. Same with data efficiency. For example, a small multi-layer perceptron can be trained on FFT outputs using from 50 to 100 samples compared to, again, the equivalent amount of 65,000 in pure ML, which is the same as the weights. So all these adds up, and that's the reason why edge AI in the past has not been that performant in low MCUs devices. Same with wavelets versus neural networks. Wavelets are just basically a specialized algorithm that go similar to FFT. But a neural network will get us very good results But this is the difference that we get. Like peak RAM usage on neural network, 76 kilobytes. With our wavelets approach, which is DSP before it goes to neural network, is 1.8 kilobytes. Now, DSP beats ML every time in this kind of computation, especially on FFTs and signal processing and all. So we always use DSP. But then we created our tool Eon Tuner, which is a big part of Edge Impulse. Eon Tuner basically takes your model and runs it through a ton of different hyperparameter configurations, ton of different device configurations. And when we made this and we run it through some of our solutions, turns out performance is not always intuitive. Turns out that neural networks are actually sometimes faster. If the device has a neural processor, sometimes it's faster, not always. There's a comparison between Cortex M7, if I'm not wrong, and the Alif's U55 with the, I think it has the Ethos U55 neural processor. And in that case, the DSP, if you see it, is the purple line, the blue line, the neural network is the purple line. The neural network on the M7 takes most of the time. On the U55, takes nothing. So neural network in this case is faster. Now, how would a user that is not necessarily an expert or even an expert know how to balance their algorithms and how to design their neural network if we didn't know? It's not intuitive. It's not always intuitive. Why? Because the variables that are involved, not only on the model side, on the algorithm side, on the data side, but then on the embedded side, memory, processors, the variables are so many that it's not even intuitive. It's not easy to optimize for devices. You need to delegate it to a tool like that can just run many times the configurations on known benchmarks, which we run on our devices, compared to your computation, and see what's better. Another lesson we've learned is choose boring tech, especially in this field. At Edge Impulse, we're in the state of the art of both ML and embedded. We don't need more tech, more states of the art. This is enough for us. So one of the main things that we spend our time doing, or that we used to, is managing dependencies all across the board, but also on, like, if you've done any Python, any complex Python, you know how hard it is to manage packages, dependencies, etc. We obviously have front ends, back ends, infrastructure, Terraforms, Kubernetes, all kinds of stuff. We try to keep it simple and use standard tech, pin down the dependencies. We are actually quite behind in most packages and most software just because we don't want to upgrade unless it's necessary. Every time we upgrade anything, every time we update, there's several days of us working on something we shouldn't be working. We should be working on the AI part. And in this field, you also deal with a lot of external third parties. Like, for example, we use TensorFlow Lite and TensorFlow for microcontrollers a lot. Turns out these are maintained by Google, by the way. Google contributes to it, but they also own it, even if it's open source. What that means is that, for example, TensorFlow for microcontrollers doesn't have a release schedule, doesn't have versions. It's just a repo that is open to the public, but you don't know if it's stable, if it's not, and it's a complex thing. So if you randomly upgrade your TensorFlow Lite, things are gonna not work at all. So it's a whole operation that we do every 6 months to get the latest changes, but also spin off a different team that just parallelly adapts it to our platform, sees what bugs are there. There's many. They don't accept contributions either. So we have our own TensorFlow Lite micro repository, which I'd argue is the most stable for the industry. at this point, more than Google's, because it works. We're on top of it. Google is not. So don't trust big tech too much. Don't trust that their packages, their frameworks, their software will save you. You can depend too much on them. You have to work at it. I have to wrap up, so I did not do a good job timing this tech. But let me kind of make one last point. Data is everything. Big AI, low AI, edge AI. Data is everything. And what we found is that as we want, we are at first we thought we were in the business of optimizing models, making them fit in these MCUs like super crazy compilers and all. Turns out we're in the business of educating customers and the industry about how to deal, how to have good data to begin with, and how to capture good data and how to label good data. We created several algorithms like FOMO AD to basically require less data, because most people come to you with observations, with photos of some industrial process or something, and tell you like, hey, I have the data. I want an algorithm that optimizes this and makes it super smart and detects this and that. But that doesn't work, because data, if it's bad data, it doesn't matter how much smarts, how much algorithms you put in, it's just not going to be good. So you have to help them by creating algorithms that, like FOMO AD is anomaly detection. Basically, it's an algorithm that doesn't need to see what is good and what is bad. It only needs what is good, and whatever something deviates from that, it will detect it. Auto labeling. People have a lot of data. It's not labeled data. Not labeled data is not useful. So we created algorithms that help. They cannot do everything, but they help auto label your data from a different set of samples. Data quality, detecting duplicates, integrations with existing tools, strong traceability, what model goes with what data, and so on. Performance calibration, creating synthetic data, that's going to be huge in the future. Basically, synthetic data created from your training samples to test your model once it's done against data that didn't exist before but has been created from your samples. And last, to finish that point, is NVIDIA Omniverse. We've been collaborating with them, and that's something that's coming with full force. This synthetic data, Omniverse is a full 3D environment that allows you to replicate the settings. Like, for example, what you see on the left, it's fake. It doesn't exist. It's just a replication in 3D, in very realistic 3D, of a conveyor belt that exists, that's on the right. And then there you can randomly program it, create any kind of situations to feed to the AI. And the AI is trained on this data, which looks like real, but it's not real, but it's good enough to infer on the real scenario. So that's stuff that we can do now because of the power of the latest devices as well. I'm good. All right. I have more to say, so get me outside of the talk, and I'll be happy to talk to you about other stuff. Thanks a lot for listening to me, and have a good conference.